Yeah, so maybe I'll start. So, good evening, everyone. So now we are back again. So this is the week 5 for reinforcement learning course in NPTEL-SWAYAM. So this week, so first I'll touch upon value iteration. Okay, so now first let me set up the problem. So the problem is I have a 4x4 grid world. And I have two terminal states. So these two states are terminal. And I have the rest of the states as 1, 2, 3, 4, 5, 6, 7, 11, 12, 13. Now my problem is I want to reach the terminal state given any state. So yeah, so could someone just say what the states are? So grid world is like you are in the grid world and you want to reach the terminal states. So randomly you can be anywhere in the grid world. And you want to come up with some actions so that if you are in this state, where should I go so that I can reach the terminal state?
And the states are the numbers corresponding to the grids. Okay. And the actions would be left, right.
So would it just go till 14 or would it also include the terminal state?
It should also include the terminal state, yes.
So let me call it T. And the action would be?
Left, right, up, down.
Okay, sure. So is it okay if I indicate it with arrows?
Yeah.
Okay. So this is done. So I'm making some more like I want to mathematize all this. So what I'm doing is, say you're in state 11 and if you take action left or right, then you end back in the same state. Is that fine?
Yeah.
So that I don't leave the grid world alone. This is just my numbers. I don't go in a cyclic way to 8. I just, if I take 11, if I take the action right, I go back to 11. If I'm 7, if I take action right, I go back to 7. If I'm at 3, if I take action up, I go back to 3. If I'm at 4, I take action left, I go back to 4. Is that
Yeah.
So now let me give you a policy. Okay, so now some policy. I'll call it the equiprobable policy. So what does policy actually give you? So it's action given any state, right?
Yes.
So action up given any state is equal to action down given any state is equal to action left given. So this is what does this mean? It means that the probability that I take action up if I'm given a state S. I hope that is clear. So I'm just equiprobable policy, like if I'm in any state, I'll take with the equiprobability I'll take all the actions. So I'm just generalizing a state policy. Okay?
Okay.
Let me write 1/4 so it is clear. So if I'm at any state, with equiprobability I take all the states. So now what we do is, so first we're doing value iteration. So we initialize values. So first initialize. Let me draw this. So this side I'll draw the values, and on the right side, on the left side I'll draw the values. On the right side I'll do the policy. But policy doesn't matter, so let's go slow. I know this will be some little confusing. So okay. So now I have. So while I'm initializing policy, I'm initializing everything with 0. Is that fine? So I'm initializing everything with 0. If your question is, does my convergence depend on what I initialize with? Yes, you are right. Your convergence depends on what you initialize with. Okay. So what is the policy I have? Now, I have the policy that I can go anywhere with equiprobability. Right? So all my, I hope this is clear. I'm not drawing these all here, but everywhere you can go, anywhere you can.
Yeah.
So now the reward structure. Reward structure is any action, reward penalty is -1. Any action
Okay.
on any state other than terminal is -1. Once I reach terminal, in the terminal state, any action I take, I go back to terminal state. So since it's a terminal state, even if I go to terminal state, even if I take some action, I'll be in terminal state forever.
Yes.
And action on terminal state, reward is 0. So it doesn't matter. Because everything goes to 0. This formulation is clear. Okay. So now what I'm trying to do is okay, this is K0. This is the first step. This is my initialization. Okay, now I need to update my values based on this policy that you see on the left. So first let us calculate V pi. Okay, I'm calling this pi 0. Let it be pi. Some V pi. V pi is also not good. Okay, let's call V of S. Oh, sorry. V of terminal state. So you know the V of S form. Okay, let me write down the V of S form first. V of S. Summation over all actions. I given S. Summation of all reward. This is clear to you, right?
Yeah.
And gamma, I'm taking it to be 1. Let it be undiscounted. There is no discounting here.
Okay.
Simple problem, so that you understand what we are actually doing. Okay, so next, okay, so now I want to calculate V of 0. Okay, maybe let's calculate V of 1 first. Sorry, this one V of 0, V of 1. Okay, so now the first summation is over all the actions, right? So what all actions could you take when you're at 1? Up, down, left, right. Okay, so when you take up action, what is the probability of you taking up action? So first, let me see. So now up action. What is the probability of taking up action?
With the probability by 0.25.
Yeah, so 1/4. I'll add 1/4.
Yeah.
Okay, now the inside term. Now you have taken action up. So what is the probability you'll end up at what state? If you are in state 1.
Then I'll go back to 1.
You'll go back to 1. With probability?
1.
1.
Yeah.
What is the reward? What is the immediate reward that I get?
-1.
Yes. Plus my gamma is 1. Now where do I go to?
It's still we are at state 1.
Yeah. So use the previous iterate and
Okay.
okay. And then now this is not over. Plus what is the other action I can do?
Left.
Yeah. Okay. Maybe left. We'll do left first. Okay. Left. If you take left, what is the probability that you take left? So pi. What is pi left of?
It gives 1/4.
1/4. To complete the expression.
Yeah, the same expression from before. Like -1 plus
Yes.
1 times 0.
Yes. And you see that anytime any action I take, it will be the same expression.
Yeah.
Because all are zeros. So is it okay if I write this as 3/4 and this? Like these are all the actions here. I could write 4/4, but yeah, like down and
Yeah, right.
so I have updated my value for state 1 as -1. Okay,
Mm-hmm.
now do you see that each and every state would be updated in the same way because symmetry?
Yes, yes, yes.
If anyone has doubt, you can ask me that. I just want to like go ahead with that minus. Everything is -1 except the terminal state.
Mm-hmm.
Do you want me to calculate the terminal state value, or is it fine if I? Okay,
Yeah, it's fine. It's fine. It'll be zero, right? Anyway.
Yeah, it will be zero. It will be zero because wherever you go, the immediate reward is zero.
Yeah.
VS is zero. This whole thing is zero. So any probability is all any probability into zero plus some probability into zero plus some probability into zero is equal to zero.
Yeah.
So E of terminal is equal to zero, and E of any state other than the terminal states is -1.
Mm.
So now when my k is equal to 1, I have my grid world would be zero, zero, -1, -1, -1, Okay, now I want you to just see what is my greedy policy if I use these values to get a policy. So what is my pi of new pi when I use argmax for this piece?
Mm-hmm.
When I am greedy using the values that I just had. So what is my new policy when I'm in state 1? I'll write it down.
Yeah.
Do you see why?
Because we are not penalizing when we are in the start state.
No, but okay, so you have the values. Now you want to pick up action. You have values of all the states. So this left hand side gives you values of all the states. Now you are in state 1.
Yeah.
If you pick action left, you go to 0. If you pick action right, you go to a state whose value is -1. If you pick down, you go to action -1. If you pick up, you go to action -1. Now you want arg max of, so your policy is arg max of A, your new policy, over all these VX.
Yeah.
So all the VX that you've calculated. So this you have to expand it as R plus expectation of gamma S prime and all. And
Yeah.
this expansion I'm sure, yeah, but I think sir stated this expression in one of the classes where he was doing value iteration.
Yeah.
So
expectation of reward given state in action.
Yes.
Plus gamma times summation of the
Yes,
next
gamma
value.
times summation of, yes. So this argmax of A, the new policy, the greedy policy.
Yeah.
Yeah. So the greedy policy is you don't care about this. You just want to minimize your. You want to go to a state where your rewards are maximized.
Yeah.
Where the value of the state is maximized.
Mm.
So the greedy for this is the left one, right?
Yeah.
So the second state, what is the policy?
Left again.
Right, I have -1. It doesn't matter really.
Yeah.
I'm just looking at the next.
Okay. Okay. So immediate one step reward. Okay.
It's not one step reward. I'm just looking at the value of the state. It's not the reward that I'm getting. It's the Now for the first step, the rewards match. So you're confused, but we'll do this iteratively and we'll see where it converges. So okay, I get your confusion, but bear with me. So this you understand, right? Except for these two states and this state, I think everyone would be
right. It's surrounded by -1s.
yeah,
so.
it's surrounded by -1, so it doesn't matter.
Okay.
Okay. So now what I want to do is I want to do the most thing. Forget this. Okay, forget this. Forget this ever existed. Okay. Now this value iteration. We'll remember this when policy iteration comes. Okay. We are not going to worry about this. Because in value iteration, you don't worry about what policy it is. You want the values to converge and then convert it into a greedy policy.
Right.
So this I have given you just for intuition, so that every time you iterate your value, you could get a policy, you could not get a policy, but in this I'm showing that you can get a policy. If you get a policy, just okay. So now k equal to 2. Okay, so could someone help me out with this k equal to 2? Okay, terminal state is going to be 0. That I think everyone is sure of, right?
Yeah.
Okay, so both the terminal states is 0. Let's do for VS1.
-1.
V1.
-1.
No, you need to update it. You need to update it. So you have V1 is equal to the same thing here.
Yeah. Okay.
So see, this is what actually servers proving class. So this is a contraction. It's an operator which takes a value, gives you another value. Gives so now your metric space is a matrix of these. So I take this matrix, I apply this operator, I get a new matrix.
Okay.
So you see the problem. You understand the progression. I'm updating
Yeah.
values in each and every.
Yes.
This is not the final value. I have not yet reached the optimal policy. I want to reach to an optimal policy. I'll reach an optimal policy when my values don't change. So I took these values, I applied this equation, the PS equation, on these values to get to the kth one state. Now I want to apply the same again, but now instead of using zeros, I would use -1, the minus issue. So yeah, let's do it. So okay, maybe I'll write down the equation once again. So Vs is equal to summation A by A given as summation S prime R probability S prime from R given as comma A, which expectation R plus gamma V S prime. This was it, right?
Yeah.
Okay. So now, what is the probability of choosing? Okay, again, same up action. If I'm state now, I want to do VS1, V1. So what is the probability I choose up action?
1/4.
1/4. Good. It's not
Updated.
0.
Yeah.
This policy I have not yet calculated. Okay.
Yeah.
So it's good. You're in the same policy. 1/4. Then next. Okay. So now, okay. Where do I end up?
If I take up action, the same state.
Same state with probability
Yeah.
1. So I'm
Yeah.
not writing the 1 again. I get -1 reward. Gamma is 1, and now my V S prime is -1. So -1
Right.
plus 1/4. Suppose now I take left.
So okay, we get 3 times the first quantity and 1 times 0.
Good. So is it okay if I write 3 and 1/4 into -1?
Yeah.
So I get -7/4, right?
Yes.
So that -1.75. Let me put it -1.7. So this gives you -1.7. Now you think that everything would be the same, but everything would not be the same because V2 would have 4 -1s.
Yeah. So it will be -2 in the next step.
Yeah. So V2 would have. Okay. Yeah. It's 4/4 into -1. So it's -2. You're right. So this would be -2. This would be -2. This would be -2. I hope it's clear.
Yeah.
What
And
would this be? Okay. Well, let's go. What would this be? The 1, 2, 3, 4th state.
fourth from where? Can you hold your pointer?
Okay. So 4th state.
Right. Okay. So it'll be my -1.7.
Yeah. -1.7. 5th.
Fifth is going to be -2.
-2.
-2.
Excuse me, sir.
Yeah.
So can you explain for V1 once more?
Yeah, sure. So,
Thank
yeah, sure. So V1, when you're okay, so you're calculating V1, the value of this state. So you're using this formula. Now my policy is that any state I've given, if I take the probability of taking an action in that state is 1 by 4. So I can go up, I can go left, I can go right, I can go down. All those actions have probability 1 by 4, 1 by 4, 1 by 4, 1 by 4. Is that clear?
Yes, sir.
Okay. And now suppose I've taken the action up. So so that means with probability 1 by 4 I did. Okay, if I take action up, where do I end up?
Outside the grid.
Yeah, but okay, so maybe you have joined later, but okay. I made a point that if I end up outside the grid world, then I end back in the same state.
Okay.
So that I don't come across a problem where if I go outside the grid world, there is no state to go. And it's not cycling. So if I start at 11, I don't go at 8. If I at 11, I take the action of going right, I end back at state 11. In state 7, if I take action right, I end back at state 7.
Okay, got it, sir.
So in action 3, in state 3, if I take left action or up action, I end up at state 3. So that is how the problem is posed. So that it makes easier calculations. So that actually what happens is these are n, you get n equations to solve. You have to solve for n variables, but I made it so that it will become very easy to.
Okay. And do we get a reward of -1 if we?
So the rewards are any action on any state you take, it's -1. But if you're in the terminal state, your rewards are 0. That's it.
Okay.
So even if you're in state 1 and you're going to terminal state, you'll get a -1 penalty. Your reward would be -1.
Okay.
But once you reach terminal state, any action you take, always you'll be in the terminal state only. So terminal state, up you take, you'll be in this only, left you take, you'll be this only, down you take, you'll be this only, right you take, you'll be in this state. That is the terminal state, how I define terminal state. Now, any action you take in this, it will be 0. Your reward will be 0. Okay, I hope that is clear. So now do I explain V1 again?
V1, yes, sir.
So with up action, I take 1 by 4. Now where do I end up if I take up action in V1?
Same state.
Same state with probability 1. Like given an action, I end up in the same state. That probability is 1.
Yes.
So probability 1. Now what is the immediate reward I get?
-1.
Yes. I have chosen this to be undiscounted, so gamma is 1. For my whole the problem, gamma is 1. 1
Okay.
into Bs prime. Where is my S prime? Where do I end up in?
Same state, so -1.
No, but what is the value of the state? The value of the state is -1.7.
Okay.
Okay, no, that okay. So this is the iteration. So sorry. Yeah, -1. So the value was -1. Yeah. And this is I calculated in K2. Yeah. So yeah, right, -1. Now, similarly, if I take left action, down action, everything would have the same equation, right?
Yes.
So I'm just writing 3 into 4, 3 times this thing, because same equation would be repeated 3 times for the up action, for the left action, for the bottom action. But
Yes.
for the right action, you see that V0 is 0. V terminal state is 0. So with probability 1 by 4, I get with probability 1 I go to the terminal state. Reward is -1, but my value of the terminal state is 0. So I am done. So 3 by 4 into -1, -1 by 4.
Mm.
So -6 by 4, -1 by 4, -7 by 4.
Okay, got it, sir.
Okay, you guys have any more doubts? You can feel free to ask. So this is how. Okay, so this you are iterating value. You are iterating the values. You are not worried about policies at all. Okay. So yeah. So maybe let me do this. So what would 1, 2, 3, 4, 5, 6, 7, 8, 11th state would be?
-1.7.
And -2, -2, -1.7.
-1.7. Yeah.
Okay. So now can you give me the optimal policies? We did it like greedy. Okay, this I'm doing just for intuition. This greedy one I'm doing just for intuition. You don't need to take that seriously, but you'll come to know why I'm doing this.
Yeah.
Okay,
So first action would be left, and then left again,
yes,
and then the same
doesn't matter.
doesn't matter, and then the other one is down,
Yeah,
down,
yes.
and then doesn't matter. The middle grid, 4 elements. Okay, never mind.
Okay, maybe I'll name
Maybe-
out the state. 1, 2, 3, fourth one.
4, 1, 2, 3, 4. Okay, 4 is up.
Yeah. Fifth.
5 is up. Up or left? Upper left.
Okay.
And then doesn't matter.
Okay.
Oh,
five,
actually,
6, 8.
okay. Maybe then yeah, 8, right? 8 is up,
Yes.
and then doesn't matter. Doesn't matter. No. Down and right.
Yeah.
Right. And then say doesn't matter.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12th one doesn't matter. Okay.
Yeah. And then right.
Okay, anyone has doubt in how we are doing the greedy policy? You can ask. Okay, I hope it's clear to everyone. Okay, so yeah, so this is the optimal policy. This is the not optimal. Sorry, sir. This is the greedy policy when you have these values. When you apply greedy. Okay, just keep in mind. And do you guys see that policy also has changed when your values have changed?
Yeah.
Make a note of that. Okay, so now let's do k equal to 3. Okay, Vt would be 0 and 0. That I think everyone is fine with, right?
Yeah.
Do you want to calculate V1, or is it okay if I just note down the values? Are you fine with it?
Noting down the values is fine. Yeah.
Yeah, I'll note down the values.
Yeah.
So give me some time because the values start getting 0, minus 2.4, minus 2.9, minus 3, minus 2.4, minus 2.3, minus 3, minus 2.9, minus 2.4, minus 3, minus 2.4, minus 3, minus 2.9, 4, 0. Okay, now can you tell me the greedy policy?
Left.
Okay, you're going from 1, right?
Yeah, 1.
Okay, left.
Doesn't matter.
Why doesn't matter?
Because both the sides are okay, maybe right. So down or left?
Yeah.
Right. Then it's up. Up or left, and then up or left.
Up or no. Doesn't matter, right?
Right. Yeah, doesn't matter. And then it's down, and then the next one should be up. Next one should be up or left.
Doesn't matter.
Oh, okay.
No, you get it. Why is
I don't
it
know.
matter?
Yeah, I know. I'm just not seeing the next value. Okay, fine. Right. Then it's down or right, and then it's down, and then it's up or right. Right.
Is there a change or is there no change?
There is a change. The diagonal values were like doesn't matters.
Oh, okay. So the change was these two, right?
Yeah.
Okay. So now you see that policy also have upgraded. Your values have upgraded, policy have upgraded. So Yeah.
So why the diagonal values are like the policy is right and down?
Oh,
Why?
okay. That's a good question. So, mm, if you take action left, if you take action right, where do you end up?
In the same state,
And what is the value of the state?
-3.
If you take action right, where do you end up?
Right, no, same state.
No, sorry, left. If you take action left, where do you end up?
-2.9.
So, which is greater, -2.9 or -3?
Okay.
You
Yeah.
want to maximize, so the greedy policy is that you have a state, you have all your actions. So now you want to pick an action so that you have a highest probable chance of going to the state which has maximum value. The value, what it denotes is maximum expected reward.
Okay.
So every time what you want to do is you want to go from a state to another state which has high value.
Okay.
I hope that is clear.
Yes. Yes. Sir.
So the greedy policy is you are not looking at the whole thing. You are just looking like, okay, I know that these values are just one of the items. It's not all the items. It's not like the actual value using the FDP. Like this is just one iteration of the value. Using that, I am just doing a greedy policy. This is just for you to understand that how do I come up with a greedy policy given a set of values.
Yeah. Okay.
So just forget about this. Just remember that your underlying policy is EP probable. And using the TP probable policy, I'm iterating the values at each and every step.
Okay.
And each and every step, how do you find a policy once you have converged? This is the way how you find a policy. But you have not yet converged.
Okay. Okay.
You have any doubts, you can ask. Like, it's okay. We can spend some more time. It's okay.
Yeah.
K4 I am giving because I didn't do the whole calculation, but it's minus 3.0, minus 3.0, minus 3.8, minus 3.9, minus 3.0. Okay, could you do these four states? I didn't do those calculations. Minus 3.8, minus 3.0, minus 3.0, minus 3.8, minus 3.8. Okay, what would 5 be? V of 5. So with 1 by 4, I have minus 1, minus 3. Okay, so minus 1 minus 2.4 plus 1 by 4 minus 1 minus 3. So 2 minus 3s and 2 minus 4. So 2. So I have 1 by 2 into minus 2 4.4 7. Right?
And the diagonal element will also be minus 3.7.
What would this be?
Let's calculate that. Let's see.
6. That is 4 by 4, right? It's everywhere is minus 2.4.
Yeah. Yes. That will be 4 on each side. Negative 4.
Okay, negative 4. We are not calculating. Negative 4, no?
Yeah.
Okay, so now could you tell me what the greedy policy is?
Left, left or down, and then up, left or up, and then left or down, yeah, and then this is going to be up or down. No, never mind, it's down, yeah. And then the next one is going to be up, 3.7, right, it's going to be up or left, up or right, yeah. And then the other one is going to be right or down.
Sorry, what? Right or down, right?
Yeah. And then down. And then up or right. Right.
Okay. So here also there is a change, right? From this, these both are changed. So these both have changed.
Yeah.
The states 1, 2, 3, 4, 5, 6 and 9. 6 and 9 have changed.
Yeah.
Yeah, so in the policy, values to every value has changed. So values it has not yet converged, but so this has changed. Okay, so do you understand the intuition behind that we are going to the optimal policy?
Yes, by minimizing the cost.
Yeah, like do you see that in the progression in the right side when the policies are getting updated? Do you see that? Yeah, so that is yeah, so if you are in exactly just right beside of the terminal state, in the first iteration you get a value and policy that I need to go to the terminal state. And these were first, like they were on the no, it doesn't matter where you go, so you can again return to the same state. Instead of taking the action where you return back to the same state, waste energy, you can go this way or this way. 2 steps, 1, 2, 1, 2.
Yeah.
It takes some effort, but the optimal is you go in the direction which is the terminal. Same this you could go anywhere, but like this is trying to fix it to go to this direction 2 step or this direction 2 step. Similar this one, it's trying to fix this 2 step or this 2 step. So I hope you see the optimal policy projection.
Yeah. I see how this is generalized versus the one that Professor done, because we have a max over actions there.
No, you are doing max over actions. The greedy part which you are doing, you don't see the operation problem as a max problem, but you are doing max over. Like how do you get this left?
No, I'm not talking about the pi. He is taking, instead of b pi, we are taking V star in the value iteration.
You don't know V star yet.
We are using V star formula. That means max over actions, expected reward plus gamma times profit.
Yeah. Okay. Yeah, I get your point. So this thing, professor has not told.
He has. That is from the way we are recovering the policy. But instead of multiplying the probabilities and taking for each probability, counting for each probability, the V for each probability. Instead, what we are doing is, for the action that will give me the maximum reward, I'll take that probability alone. According to the value iteration that
actually I have simplified the problem such that you don't get that probability. So the MTP is very easy. Once you fix an action, you win probability 1, you're going somewhere. The MTP could be more, so then you get that what Prof has taught you. Because then you get multiple actions, because each action could give you, so you take the action with the probability, highest probability of going into a state which has high value. So I hope I'm not confusing you there by simplifying the problem deterministically.
No, not at all. Good intuition.
Okay. So now I'll tell you that in value iteration, what happens is, after K4, K is equal to 10. So I'll wait for K is equal to 10. I ran a code. You guys can run a code for this. I don't have that. Maybe I'll show you. So this is 0 0 minus 6.1 minus 8.4 So if you do the greedy of this, it is the same policy, but the values keep changing. The policy doesn't update more because there's nothing more to update. You have to use the optimal policy at k is equal to 4, but the values keep on changing.
Right. This calls for another question. I was going through this blog. I raised the question in the forums itself.
When to stop?
So, yeah, right. So it cites some book from Dimitri. So we have reached the optimal policy even before the value function is converged. So let's say that's the case. Then we wouldn't need to update the value function anymore. We should have ideally stopped when we have got the optimal policy.
Yeah.
But when do we know when to stop?
Yeah. So you have actually you have now recreated the invention of policy iteration. So that's natural progression, right? So first people were like, why do I want to do this whole step of calculating the policy at each and every one? I'll just calculate the value addition. So instead of calculating the policies at each and every step, go on calculating the values. If my value converged, I am sure that my policy has converged. That is one guarantee, right?
Yeah.
But when your policy has converged, you have no idea of when your policy has converged. So came up policy iteration. So I want to just check whether I have converged or not. So you can do this, like you can do multiple of things in R. So value iterations tells you, the algorithm value iteration tells you that forget about policy, take any policy, initialize your values, apply the same operator on it over and over again, get new values. You will reach a fixed point.
Yeah.
It is a fixed Banach theorem. You are in the metric space of all those values. Blah blah blah. You will reach a fixed point. If you have converged in the values, the theorem says that if you have converged in values, I will guarantee you that you have converged in policy.
Okay.
Okay. So when to stop is when you have converged in values. That is technically when you want to stop for value iteration. But as you said, my policy could have converged like way long back.
Yeah.
When my values have not yet converged on. But I'm just doing it because my theorem says that if my values converge, then my policy is converged. It does not say that my policy converged implies that my values also, like that also is there, but when my policy start converging, then itself my values will converge. That it does not say.
Right.
I hope I'm clear.
Yes.
And eventually this policy would converge. It would converge to some. It will converge to some. You can go and have a look in Sutton and Barto. I think Sutton and Barto also states this. So 0 minus 14 is 20. Okay. I think I'm running out of time. Even you will converge at these values. This will take some how it sounds many iterations, but you will finally converge.
Okay.
You will converge and then you will stop.
Yeah.
Converge matlab they will update but with very less. Or convergence is you're right in that. There is a debate in how. No, there is no debate. Like you know when values will converge, right?
If I apply the L operator again, I'll get the same.
That is your ideal case where you want, like, if I apply the L operator, I would get again the same V.
Yeah.
That is my ideal case, but you don't need to do that. You can take an epsilon.
Yeah, epsilon times 1 minus gamma by 2.
Gamma, yeah. The theorem proves are clear. So
Yeah.
if you take that threshold, and you see that all your values are in that ball, like in that is less than that radius. So
Yeah.
so difference between the two values is less than the epsilon times gamma by 2 into 1 minus gamma by epsilon by 2 into gamma is less than that, then you're converged, you're stopping. That implies that you have converged in policy.
Right.
But that will take some time.
Yeah.
Policy iteration is way quicker.
Right.
So now this value iteration is done. You guys are making out value iteration with estimates. I actually have taken a very simple problem, but calculating this term is very difficult. No, not very difficult, it's easy, but you need to be sure that you put the probabilities correctly.
Yeah, right.
Because now I'm making it, this whole MDP I'm making it deterministic.
Yeah.
When I fix
And if the
it,
environment was stochastic, then I'd be in a lot of
if
trouble.
the environment stochastic, this calculating is a lot of trouble.
Yeah.
But you can code it up. Like, it's just computational problem.
Monte Carlo.
No. Why? Okay.
If P is not given, I would be running the sample.
Okay, if P is running Monte Carlo, I'll come to that.
Okay.
Okay. But for you're right. Actually, it's Monte Carlo. If P is not given, but here we are assuming that P is given, and I'm showing that your MDP is given, and then your value is converged. In policy iteration, what you do is, okay, we'll do the same problem in policy iteration. Now, so now I've taken first it is equiprobable case, right? Equiprobable policy.
Yeah.
I initialize values k equal to 0, and then okay, and then this is my policy. Like this is my policy. Okay, so now I evaluate this policy and update the v values. So this is it clear? Okay, so now this updation of one step is policy evaluation.
Yeah.
Okay, and then I update my policy. This is policy improvement, where I use the grid. Now, while updating, I don't use the equiprobable policy. I use this new policy I have, which I have uploaded, which I have done by greedy. So now you see that all these values would change.
So each time I'll be taking different actions for the same.
Yes. So now my pi of AS would change.
Example case.
Actually, I didn't hear.
No, I was just saying that at each iteration we'll be taking different actions.
At each iteration, different actions, your pi would change, your policy would change.
Yeah, according to pi.
According to pi, yeah, like greedy, this thing.
Yeah.
So now you update instead of updating using the equiprobable case, your pi is now. So now what would change is your v1 would be, for this case, would be you have only one action. So pi of a given 1, state 1 is only left. Everything else is 0. So this is policy iteration, and this is value iteration. So you have probability 1, you go left, and then you have -1, -0. So it's -1. So this stays at -1. Is that clear?
Yeah.
And similarly, since you have these stays in, this stays at -1, this stays in, this stays in, this stays at -1, this stays in, this stays at -1. Then again you go to greedy, you see that this is the same as last time. Left, these all will stay same. So now again you calculate, now you have a new policy. You calculate the new values based on this policy, not the previous one.
Right.
So you basically run a loop of, so I initiate pi 0 and v 0. I do policy evaluation, I calculate v pi 0. Using this pi 0, I calculate a v pi 0. Then I do policy improvement. pi 1. This is done greedily. Then I evaluate policy evaluation B pi 1. Then I policy improvement greedy. I do P pi 2. This continues.
Right. So essentially what I do is, instead of keeping pi stationary as before, in policy iteration pi is not stationary anymore, and instead of using v for watching conversions, we say that if at time step n plus 1 I have the same policy as the policy at time step n, then I'm finished.
And you see why this is better than value iteration, but why
Yeah.
value iteration is preferred.
Right. So at each time step I'll have to calculate the policy and
Policy,
again and
yes,
again.
yes. Then that it's monotonous, right? So calculate, keep on, you put the computer to calculate just the values, it will calculate all the values, you know it's calculated, you're done.
Yeah.
Okay. Instead of calculate the values, then again go back to calculate the policy, calculate the values, calculate the policy, improve. Again, this is what Sir has mentioned in the class as generalized policy iteration. Sir's policy iteration also is similar to what I tried to do here by showing the policies for each of the every values. This version that I have shown is generalized policy iteration. This is actually how it's done.
Okay.
So this also I think answers your question as when to stop. So the value
Yeah.
iteration with the policy, if you can do like you can do just value iteration, but you can do at every step you can pull out a policy and see, okay, what is happening to my policy, but update the values based on just one policy, the first
Right.
policy that was shown, and see, okay, but my policy is converged, but my values are still not converged. They go on. It could be happen that both converge at the same time. It could happen. Depending on what initial condition you choose. Okay. The next thing is, okay, why am I looking only at the values? Maybe generalized policy iteration is maybe I can. Okay, policy iteration is calculate the value, look at policy. If it is better, use this or use that or some. I think there is something, but generalized one is sure. Is if you use greedy, you will always create a better policy than the previous one.
Yeah.
That proof has Sir done in class.
Yeah, I think it is done. Well, can you like give me an example of what it would be?
Okay, so I think Sir has done it. Okay, so here I am choosing equal problem for all states, right? This
Yeah.
is my first policy. My next policy is I have changed the policy.
Yeah.
I am applying greedy. Now my claim is that this policy is better than this policy. It will always be better than or at least equal.
Yeah, I think this is done.
And then you apply the L operator on values, you get a new policy greedily.
Yeah.
That will always be better than the previous one. So you're always approaching a good policy. You're either approaching a good policy or you're at the same policy which is as previous, which gives you the previous one. Let me pause for like 2 minutes. This policy iteration. So I'll not do dynamic programming this time, but if you guys have any doubts, okay, I'll give you a reference. So you can look at Bertsekas, Dynamic Programming and Optimal Control, Chapter 1, Volume 1, Chapter 1.
Okay.
Bertsekas, Dynamic Programming and
October.
He has 2 volumes on it. So read the volume 1. Volume 1, chapter 1. Chapter 1 is on dynamic programming.
Okay.
His notations are very difficult to reinterpret. Half the time we would go to like, okay, what are the demands? Mapping the notations. He has used different notations. I think he uses G for something, capital G for returns of like total returns. Capital J or something, and there instead of maximizing rewards, all of Bertsekas thing is minimizing cost. So I think, but both are the same, so you can do the same thing.
Yeah.
So yeah, the first chapter 1 has good problems on dynamic programming if you want to.
Okay. Please do that.
So next, I want to quickly do an Marco Monte Carlo, sorry. Monte Carlo. So Monte Carlo, very simple examples I'll do. Okay, I have an MDP with two states, A and B, A, B terminal state. Okay, A, B terminal state. I have an episode 1. I sample it. I get A, I get reward of 3, 2, minus 4, plus 4, minus 3. This is episode 1. Yeah, you guys understand episode, right? Minus 2, plus 3, minus 3. Okay, so now calculate BA and BB using first visit MC and every visit MC. Okay, I think sir has not told what first visit MC and every visit MC is.
No, I did. Yeah, I think he did. Yeah, first visit means only the first time will be counted. Every visit means every time a state occurs, I'll consider from that state as a separate trajectory.
Okay, so could you tell me VA when it's first visit?
Okay. How should I be calculating it? Is it just?
Okay, so now you have two episodes, right? In the first episode, you hit A here.
Yeah.
Add up the rewards after that till you reach terminal. So you
Okay. Need to 1 plus 4. That's a 4, right?
Okay, which one?
After A to B. After
There is no A to B. Where is A to B?
before the terminal state.
This is plus 4.
Okay.
This is also minus 4.
5, 2
This is
and
right?
yeah.
And in the second episode, this is when you hit 1 for A for the first time. So calculate the rewards from there, like assuming that is the first hit.
2 plus 0.
Yeah, 2 plus 0. Now average it over the 2 episodes. 2
Right.
plus 0 by 2. So 1.
1.
VB.
B, okay. So minus 4 plus 4 minus 3, negative 3 plus minus 2 plus 3, 1 minus 3, negative 2. Yeah.
Okay, so
Minus 2.5.
what does this tell you of the MDP? That B is a very bad state because every time you go to B, you come out with a reward which is of negatives.
Yeah.
So this is like this basically what is like if you have infinite number of episodes and you do this thing infinite number of times, you calculate the ESVPs, then you will reach to the actual value, true value of the state. That is what Monte Carlo says. I can't have infinite number of episodes, but you can code it up. But what you need to calculate is what I say.
Right.
Okay? Every visit.
So B would be 3, 2, 5 minus 4. The first one would be 2 plus 2. Then again, I'll start from the second A, right? 2 plus 2, 4.
Yeah. You're right. So calculate terminal. Then you start from here. Calculate terminal. Calculate terminal. Terminal. So you have four cases, right?
For V of A should be 2 minus 1 plus 1.
4 cases, right?
1, 2, 3 cases for the first one, and then right, yeah, and then 3.
Okay,
Yeah.
plus 0.
This is plus 0.
By 4.
By 4. It's moving 0.5.
Similarly, VB also you'll get minus 3, minus 2, minus 3.
B is also 4, right?
Yeah, 4. Yeah.
Minus 3, minus 3, minus 2, minus 3.
Minus 3, minus 2. Okay, minus 3, minus 3, minus 2, minus 3. Minus 3, minus 2, minus 3.
Minus 3.
1 by 4. Here also using that these better. But yeah, so these both would give you different P's, but if you have infinite number of episodes like this, it will eventually converge to the same one. Both of them will converge to the same. I'm not doing both that calculation, you can do it up. Like you can set up an environment where you have underlying NDP and just do trajectories, multiple trajectories. Each trajectory you do, just keep on updating these equations.
Okay.
Okay, so now a bonus question to you guys. Okay, so what happens if I have episode 3? Okay. B, minus 2, minus 3. How does my VA change for the first visit MC?
VA shouldn't change.
So that is what VA shouldn't change. VB also shouldn't change. Every visit anyhow it's not changing. But how will VB change?
VB will have 2 more terms.
No, one more term. First visit will have one more term.
Okay, first visit will have 1 more term. Every visit will have 2 more terms.
Yeah, I hope that is clear.
Excuse me, sir.
Yeah.
So, what is the difference between both the first visit and every visit? Like, I know the method we are doing, but why is any one of the better, or why we are doing, like, why we have two?
Yeah. So in some cases, first visit becomes computationally hard. In some cases, every visit becomes computationally hard. So it's basically what you're trying to do is you have multiple episodes. So actually, what you want to do is you want to only do it once, and as limit t tends to infinity, you want to explore and exploit each and every step. That is what you want technically. But since you don't do that, what you do is you introduce a terminal state. You let the MDP go to terminal state, and you do episodes. So you make it run on one processor, second processor, third processor, fourth processor. The more number of episodes, the parallel you are learning, right? So first visit, what happens is sometimes what happens is if your states are less, but you have more number of actions, then I think actions. Then what happens is first time visit calculation becomes simpler. Okay, I'm not sure, but there are cases where first visit becomes computationally easier than every visit. Sometimes every visit is computationally easier than first visit. This is just a computational thing. Like, do you want to? The theorems are both converges, right?
Yeah. Yes.
Both converge to the limit. Now, which you want to use is your problem specific. Which you feel that it's not you feel. It's actually there is a thing I forgot that. Yeah. So when first visit is computationally easier, when every visit is computationally easier. I hope I answered your topic. I'm
network.
Hello?
Sorry.
Yeah.
I'll look up in the video. Yeah, my net was disconnected. I'm very sorry.
Oh no. Yeah.
Look up in the recorded audio.
Okay. I can tell you again. It's just computationally. In some cases, first visit might be better than every visit. In some cases, every visit might be better than the first visit. So computational things. But Monte Carlo says that even if you calculate first visit, Monte Carlo it will converge. Even if you do every visit, Monte Carlo it will converge. Convergence is guaranteed for both.
Okay.
So there is no other reason other than computational requirements.
Computational and convergence also. Rate of convergence.
Okay.
I think Sir has touched on these subjects in the lecture, but he has not given proofs for them.
Yes, he said what first visit and every visit is. That's it.
And he gave why first visit and every visit is better. That proof was practical only. It was not like some theoretical stuff where you miss out something. You don't miss out anything.
Yeah.
It's just like computationally you have to do more number of terms. I think it's in the first visit you have to have computationally more number of episodes.
Yeah.
In every visits you don't have to have computationally many number of episodes, but you need to sample it longer times or something like that to change the same convergence.
He also said that if some rare term comes, then every visit will actually extrapolate it or something like that.
Actually, it's not like first visit is always better than every visit. There are pros and cons to both. That's why both are used.
Yeah.
Is your doubt clear?
Yes.
Yes.
It's more problem specific. Like you give me a problem, I'll say okay, which one could be better. You try both and you see that okay, first visit converges very quickly, every visit converges very long. Or maybe for every visit convergence I need more number of for first visit convergence I need more number of visits. Maybe you have an MTP where every time you are going, probability of going to one state is very high, other state not excluding so much. Then instead of first visit you do every visit.
Okay. Thank you.
You guys have any other doubts? You can ask. I'll stick for 5 minutes. Or you can attend Manav's tutorial. I think Manav's tutorial also okay, yeah, you guys can go to Manav's tutorial.
Maybe we have more than one tutorial each week, right?
Yeah, so
I don't think this is enough.
Yeah, you have two, right? Me and Manav.
Yeah, Manav, I think he mainly focuses on the practical side, right? I've seen him doing the code.
Manav does the code. I think this time he'll do the code for MDP. I'm not sure if he has prepared a code. Yeah. But you can, if you want more code related stuff, even I can speak, but
no, I want more theory in fact. Yeah, fine. Maybe I'll ping you on the forums.
Okay, so
if I have any doubts.
Yes, you can ping me on forum. So